they have a lot of problem in GI tract. Immune cells actually they are not activated, and they lose actually some melanin in their skin, and also bone marrow also have a problem. So as a result, when individuals are taking the anti-cancer or chemotherapy drugs, they can have an experience side effect including anemia, which bone marrow actually is affected, and RBC and YBC production is less, scaly skin, GI tract disturbance, immune deficiency, and also hair loss. Related to pyrimidine biosynthesis, did you study the urea cycle? Okay, urea cycle, at the first step of urea cycle, we had the enzyme, which name was carbamide phosphate synthase. Actually, at that step, you learn we have two kinds of carbamide phosphate synthase. One of them is mitochondrial form and is for urea synthesis. And the second is known as a carbamide phosphate synthetase type 2, which is the cytoplasmic form. So in urea cycle, CPS used CO2 and NH2 and ATP. But here, instead of NH2, we have a glutamine. So CO2, glutamine, and ATP. By carbamide phosphate synthetase type 2, produce carbamide phosphate. And carbamide phosphate, by receiving aspartate, okay, they become uric acid. Uric acid, or OMP, by receiving the phosphate, is the first pyrimidine nucleotide. Then, by receiving PRPP, so it has a differences with purine producing. In purine producing, first of all, we need to have a PRPP, and then we can add our atom. But here, first of all, we produce a pyrimidine base, then we will add a PRPP, or phosphoribosylpyrophosphate synthase. Then, by using one CO2, UMP is produced. So then, from UMP, we produce another pyrimidine. For example, they become UDP and UTP and change to the CTP by receiving amine from glutamine. For production of thymine, because you know thymine is just used for DNA replication, and we need a deoxyribose instead of ribose. So UDP convert to the DUDP or deoxy-UDP by an enzyme which name is ribonucleotide reductase. Ribonucleotide reductase just can convert the diphosphate form of nucleotide to deoxy form of, for example, UDP to DUDP, ADP to DADP, GDP to DGDP, and like that. Just can act on the diphosphate form. It was a question. Ribonucleotide reductase have an effect on which of these molecules? AMP, GTP, GMP, GDP. For diphosphate form. And hydroxyurea is the inhibitor of ribonucleotide reductase. Then DUDP changed to the DUMP, and DUMP produced DTMP. By what? By receiving methyl group from tetrahydrofolic acid. And we have a thymidylate synthetase here, which can inhibit it by 5-fluorouracil. It was questioned. 5-fluorouracil inhibit what kind of following enzyme? Thymidylate synthetase, adenine ribonucleotase, adenosine deaminase, guanosine phosphoryboside pyrophosphate transferase. Like that. So, thymidylate synthetase. In the other sides, we have a methylene tetrahydrofluoric acid, and when they give the methyl group to UMP, they become dihydrofolate, okay? And this dihydrofolate should actually again do reducing or reductase to produce methyl tetrahydrofluoric acid. So dihydrofolate should convert to tetrahydrofluoric acid. It's known as an activation, actually, reaction. This activation reaction needs dihydrofolate reductase. And metatherside in eukaryotes and actually 3-methyl-prene in prokaryotes inhibit the dihydrofolate reductase. So metatherside as an anti-cancer or chemotherapy agent inhibit dihydrofolate reductase. When we inhibit dihydrofolate reductase, we can't have a tetrahydrofluoric acid as an active form. When we don't have tetrahydrofluoric acid, we can't produce thymine. When we don't have thymine, also we can produce DNA and cell replication cannot occur. So for producing both pyrimidine and purine, we need tetrahydrofluoric acid. For producing pyrimidine, we need all of these except glutamine, glycine, aspartate, carbamate phosphate. Which one? This is a carbamate. This is a glutamine. This is an aspartate. Glycine. So glycine just is needed for purine. It's pyrimidine actually. Yeah. Just for purine. For example. The second, what is the actually similarity between pyrimidine and purine production? Glutamine, glycine, or actually carbamate phosphate, or other thing that's something other.
Glutamine?
Yes, exactly. Glutamine and aspartate both are actually similar for production of oil. The question are like that actually. I gave some kind of solution. And again, carbamate phosphate synthesis type 2, which produce carbamate phosphate. And this is the other reaction of production pyrimidine. At final, we need glutamine for producing CTP. It's not needed. It's actually regulation of pyrimidine synthesis because it's somewhat difficult to memorize all of these reactions. You don't need to learn that slide, and this slide also is again required to do this. But this slide is important for us. Actually, I mentioned ribonucleotide reductase is inhibited by hydroxyurea, and thymidylate synthetase is inhibited by 5-fluorouracil, and dihydrofolate reductase is inhibited by methotrexate in eukaryotic and 3-methylprene in prokaryotic cells. And it's their function. One of the important enzymes, as I mentioned, is a ribonucleotide reductase. As I mentioned, just act on diphosphate form and produce deoxy form of actually a nucleotide. And finally, DUDP becomes DUMP and DTMP. So all of these four are used for DNA synthesis. In addition to hydroxyurea, as I mentioned, they inhibited by also DADP and DATP. Just remember that DADP and DATP. If we have a lot of concentration of ATP or ADP, what's happened? So, ribonucleotide reductase is inhibited. So we don't have a deoxy form, and we can produce DNA also. Okay? So what's happened? If we cannot degrade the ATP and ADP, okay, they lead to the
Increase.
increase or decrease.
Increase.
Decrease the
Decrease.
production because they inhibit ribonucleotide reductase.
If they are degraded,
If
means they are
they are degraded, they can't inhibit it. If they remain actually in high concentration, they inhibit ribonucleotide reductase. Okay? Got it?
Yeah.
So for this reason, if what kind of enzyme at the first step of purine degradation, especially adenosine degradation, we need for adenosine, for degradation, not for synthesis. Adenosine deaminase. Adenosine deaminase. Okay? If adenosine deaminase cannot do its function very well because of adenosine deaminase deficiency, what's happened? ADP and ATP increase. Ribonucleotide reductase decrease. We don't have enough this. We can't have DNA replication. What kind of cells actually are affected in this? Immune cells. And they lead to the severe combined immunodeficiency disease. So it's the correlation between adenosine deaminase deficiency and severe combined immunodeficiency.
So it's not immunotherapy, right?
Also, it can be due to the chemotherapy agent, but specifically for adenosine deaminase deficiency, we can see this situation also. So the next pathway is related to salvage pathway. In de novo synthesis, the synthesis of nucleotide begins with their metabolite precursor amino acid, ribose phosphate CO2, and one carbon unit, which they are actually tetrahydrofolic acid. But in salvage pathway, we have an activated ribose as a PRPP, and we will add the bases and produce nucleotide. So we need PRPP and adding base, and we produce a nucleotide. One of them is actually for adenine. Let's read it here. When we are going to recycle or salvage adenine, by adding PRPP to adenine, we produce ALP. The enzyme is APRT. APRT, adenine phosphoribosine transferase. But it's not very important because it generates a little of adenine. Adenine phosphoribosine transferase or APRT. But here we have the two bases, hypoxanthine and guanine. And we are going to add phosphoribosine pyrophosphate. The enzyme name is hypoxanthine guanine phosphoribosine transferase. HGPRT. The name somehow is, the length of the name is hypoxanthine guanine phosphoribosine transferase, but you can abbreviate it as a form of HGPRT. What is do? It's recycle hypoxanthine as a form of AMP, IMP, and guanine as a form of GMP. And IMP, as you learn, can produce both AMP and GMP. And most part of AMP is produced from that pathway and IMP. So, this is the function, guanine and hypoxanthine and also adenine. By receiving phosphoribosine, they can actually produce GMP and AMP. This enzyme is so important for us. HGPRT, hypoxanthine guanine phosphoribosine transferase. If we have a dysfunction in these enzymes, it leads to the syndrome which is known as the Lesch-Nyhan syndrome. What do you think about Lesch-Nyhan syndrome? What is actually the output? If we can't recycle these nucleotides and incorporate them into the DNA, what's going on to happen? Then if these bases cannot be used for DNA synthesis, what is their fate? Exactly. They degrade to the uric acid. So uric acid production is increased. And what kind of disease is like goat. So one of the actually side effect or actually sign of Leishman syndrome is goat disease because they degraded to uric acid and uric acid concentration is increased. Related to pyrimidine actually salvage, it doesn't actually important for you. Do not talk about pyrimidine salvage. But related to a drug which we can use as anti-cancer or other thing. One of them is a pyrimidine analog, 5-fluorouracil, as you saw, is inhibited thymidine synthase. Okay. Amino acid analog, azacin, inhibits the synthesis of CTP. Folic acid analog, methotrexate, inhibits synthesis of thymine. And nucleic acid analog, arabinosid, cytosine, or RAC, inhibits synthesis of CDP. All of them are. And related to their structure, just you don't need to memorize them, but for example, this is azacin and this is glutamine. This is glutamine, this is azacin. They are so similar together, but here we have an acid. This is actually known as an acid. So if instead of glutamine we have an azacin, they can inhibit purine and pyrimidine production. Related to methotrexate, this is a folic acid structure, and this is methotrexate. Just instead of actually this H group in folic acid, we have a metal group in methotrexate. By adding metal here, it's become an anti-cancer drug. And again, it's their structure, and methotrexate inhibits dihydrofolate reductase. And 6-mercaptopurine is an analog of hypoxanthine. This is a hypoxanthine, this is a 6-mercaptopurine. Instead of hydroxyl group, just as a sulfide group. And 6-mercaptopurine inhibits de novo synthesis and salvage pathway both. Okay? So for this reason, because it's inhibit de novo synthesis, also the production of uric acid is low and hypouricemia is active. All the time when we use anti-cancer drug or chemotherapy agent or actually during cancer disease, because the rate of DNA degradation is increased, purine catabolism is increased, and uric acid also is increased. But with one exception, is that 6-mercaptopurine. Because it inhibits purine synthesis also, the uric acid production is decreased and leads to the hypouricemia. And related to catabolism of purine, you saw that we need adenosine deaminase deficient, adenosine deaminase or ADA. If we have adenosine deaminase deficiency, it leads to the severe combined immunodeficiency or SCID. Because the oxyadenosine is accumulated and ribonucleotide reductase is inhibited. This is actually the explanation for adenosine deaminase deficiency. Actually, every semester is a question. Which kind of actually this deficiency of which kind of the enzyme lead to severe combined immunodeficiency. Adenosine dominance. Adenosine dominance deficiency. And related to actually SGPRT function, as you can see here, hyperxanthine and 1. By SGPRT can recycle and use for production of EM. If actually look at this, 90% of them are recycled by SGPRT, and 10% just produce uric acid. If we have dysfunction of this enzyme, all of them go to the uric acid production, and uric acid is increased. To inhibit xanthine oxidase, we need allopurinol. Allopurinol inhibits xanthine oxidase and decrease uric acid excretion. Lesch-Nyhan syndrome actually first time described in 1964 by Michael Lesch and William Nyhan. For this reason, it's known as the Lesch-Nyhan syndrome. It's actually due to the lack or defect in HGPRT enzyme, and because it's sex-linked metabolic disorder, we have this. This is just only in male, in man. And loss of HGPRT lead to elevated PRPP level, and also the production of purine is increased by PRPP level, as I mentioned at the beginning of the class. They have mental aberration, and also they have self-mutilate. What does that mean? Self-mutilate. Yes. Do you know about self-mutilate? When someone actually bother himself, actually hit or actually do something for lips and actually harm its hand, all of them like that. Okay, it's known as a self-mutilate. Why they actually do this kind of self-mutilation? What is the reason? Because uric acid, okay, become a crystal, produce a very, very tiny crystal. They like a needle, okay? They are like that needle. This is sodium urate crystal. And these needles accumulate in actually finger, in soft tissue, in kidney, others. And when actually you feel a needle is in your finger, you just want to actually mutilate it. And for this reason, they actually have this kind of sign.
Patient feels allergy?
Allergy? No, it's not related to allergy. It's related to that actually needles, which they need, they actually produce a lot of pain. It's, for example, especially in joints, in a dash finger, and actually thumb finger in actually their leg, this finger and this finger. Also, uric acid can accumulate between joints, ear of some actually finger, in addition to finger, also in their ear and actually their hand, this side, this position of their hand. Uric acid is accumulated, and this is known as a gout. What are the reasons of gout? The causes of gout can be divided to 5. One of them is kidney disease. If we have dysfunction of kidney, we can't excrete uric acid, so uric acid accumulate in blood. Then, second, cancer chemotherapy. As you learn, they excess nucleic acid degradation from the tumor cells. So because we have a lot of purine and we can produce a lot of uric acid in chemotherapy instead of 6-mercaptol purine. And elevated PRPP synthesis. As you saw, when PRPP is high, PRPP itself increase the purine production. An inhibitor of defective PRPP amino transferase, as you saw, if we can't inhibit aminotransferase, also purine synthesis is increased. And deficiency of salvage enzyme HGPRT, as you saw, when we couldn't to recycle them, they go into degrade and also they increase the uric acid, which is known as a hyperuricemia. The normal reference range or concentration of uric acid in our body is between 3 to 7 milligram per deciliter. And the concentration more than it is known as a hyperuricemia, and less than it known as a hypouricemia. Allopurinol actually is used for treatment of gout. This is hypoxanthine. This is allopurinol. If you look at it, just in the position of the nitrogen and carbon is changed in allopurinol. And because they both are precursor of substance of actually xanthine oxidase, when xanthine binds to the allopurinol is inhibited. So it can produce uric acid more. But related to hypouricemia, what do you think? What type of actual dysfunction or reason can be linked to hypouricemia? One of them was 6-mercaptol purine, as you saw. 6-mercaptol purine because it decreased the purine synthesis lead to hypouricemia. And the second can be what? Yes, let's do actually. If we have a severe liver disease, we can produce enough purine, also hypouricemia is high. If we have defective renal tubular reabsorption, as you know, all of the substances in glomerule are going to be filtered, and then 90% of them react. If we have a dysfunction of reabsorption in a tubule in kidney, it leads to actually we lose those material. We have a syndrome which is known as a Fanconi syndrome. Fanconi syndrome is one of the reasons of hypouricemia because it leads to excrete uric acid by tubule dysfunction. It was many times questioned. Which one of the actually following lead to the hypouricemia? Fanconi syndrome is one of the actually reason of hypouricemia. And chemotherapy with 6-mercaptol purine. And finally, our treatment with allopurinol. If you overtreat, also because they inhibit uric acid production, uric acid concentration is decreased and hypouricemia is occurs. And the last slide is that all of this disorder related to purine metabolism. As you learn, gout can be used to the PRPP synthesis, HGPRT, or enzyme we have here, glucose 6-phosphatase. Just I wanted to you tell me why deficiency in glucose 6-phosphatase lead to the gout. Do you remember what was the glucose 6-phosphatase? During the actually glycogen storage disease. Okay, then the disease name is a von Gierke disease. Von Gierke disease. Why von Gierke disease led to the hyperuricemia? This is the actually understanding the content of biochemistry. And when you could to answer this kind of question, you can be sure about actually biochemistry understanding. Because as you know, glucose 6-phosphate can go to different pathways. If one of the pathway, which is glucose 6-phosphatase, is inhibited, go to the other pathway. And other pathways is a pentose phosphate pathway and produce ribose phosphate. Ribose phosphate produce PRPP, and PRPP increase production rate of purine. And when we have a increasing purine production, also we have a hyperuricemia. Is the reason. So thank you for listening. Hope you enjoyed, but I'm not sure.